Hi, this is Brad Strabig. Last time we talked about acids and bases, their definitions, and the relationship between acids, bases, the hydrogen ion concentration, pH, and pOH. This time we're going to look at what happens when we add a strong acid to an aqueous sample. So a strong acid is an acid that completely dissociates in water. We can determine the pH of a solution from a strong acid if we know how much acid has the concentration of the acid added to that solution. So in this example problem, we are asked to determine the pH for a 1 liter solution to which the strong acid, HCl, hydrochloric acid, has been added, so that the total acid concentration in the 1 liter solution after the acid has been added is 10 to the minus 3 moles per liter. The first step in most engineering problems, and this is no different, is to define the system boundaries. In this example, we have a 1 liter container of solution. We'll represent that 1 liter aqueous solution below with the circle below. So to start with, we have a simple solution of water. As in our previous example, most of the water in water is water, or H2O. But also in that aqueous solution, we're going to have 10 to the minus 7 moles of H plus and 10 to the minus 7 moles of OH. This is before we add anything to the aqueous solution. From the pure water, we're going to add the hydrochloric acid. The definition of a strong acid is an acid that completely dissociates. So the HCl, when added to solution, is going to form the H plus and some Cl minus of the anion in solution. The total concentration of the acid in solution is going to be 10 to the minus 3. And in this case, we will have, because it's a strong acid, no HCl molecule present in the aqueous solution. Step number 2 then is to identify all the chemical species of interest. In any aqueous solution, we're going to start with water, H2O, H plus, and OH minus. In this case, we've added more H plus, so we're not going to write that down again. We don't have 2 H plus. H plus acts as a variable in our analysis. So just like you wouldn't, if you have X and you add some more X to a solution, we'll have to find how much X is there. Rather than using the variable X, we're using the term H plus for one of our variable identifiers. That means we've added some of it to solution to the H plus that was already there from the dissociation of water. And in addition, we've added, the only other ion we've added is the negative ion of the chlorine. And again, the total concentration of acid that we've added is 10 to the minus 3 moles per liter. So in our species list, we have water, the hydrogen atom, the chlorine anion, and the hydroxide anion. The next step is to write all the chemical equations and constraints for the system. These may include the equilibrium equations, the electroneutrality equations, and the mass balance equations. Recall from our previous discussion in the textbook in equations 2.43 that for a strong acid, any strong acid HA is going to completely dissociate so that the concentration of the protonated acid HA is approximately 0. If we have 1 mole of HA that we start with, we'll end up with 1 mole of hydrogen ion and 1 mole of the anion in solution, or the conjugate base. In this case, we started off with a concentration of 10 to the minus 3 moles per liter of the acid added to solution. So that means we're going to have added 10 to the minus 3 moles per liter of H plus and an additional 10 to the minus 3 moles per liter of the conjugate base, in this case, the chlorine ion. Recall also our definition of pH is equal to the negative log of the hydroxide ion. So in this case again, the total concentration of the acid added to solution is 10 to the minus 3 moles per liter. The next step, step 4, is to make any simplifying assumptions that might be possible. In this case, since we have a strong acid, we've added that to solution, we know that our strong acid is going to completely dissociate, so the only ions we've added are additional H plus and the new negative anion, chlorine to solution. We also know that the total concentration of chlorine in solution is going to be 10 to the minus 3. We know from electroneutrality also that the sum of the negative ions have to equal the sum of the positive ions. Because we've added 10 to the minus 3 moles of chlorine and 10 to the minus 3 moles of H+, we know that the chlorine ion concentration is going to be approximately equal to the H+ concentration because the amount of the hydroxide ion is so small. It started out as 10 to the minus 7, and it's going to get lower. The hydroxide ion concentration is going to decrease because we've added an acid to solution. Thus, the concentration of the chlorine ion is equal to the concentration of the hydroxide ion, which is equal to the total concentration of acid added to the solution, which is 10 to the minus 3 moles per liter. In this equation, we were asked to find the pH of the solution, so we've determined the hydrogen ion concentration is equal to the chlorine ion concentration, which is equal to 10 to the minus 3, so the negative log of 10 to the minus 3 is 3. Thus, the pH of the solution is going to be 3. Let's look now at an example outside the laboratory in the environment. In this case, we can look at nitrogen oxides in the environment. They're emitted through biological transformations and also through the use of nitrogen-based fertilizers and from some fossil fuel emissions. The concentration is much less than that in carbon dioxide, but it is an influential greenhouse gas, which we'll discuss more in Chapter 6. The nitrogen oxide also has a very long residence time in the atmosphere, and it absorbs a relatively large amount of energy. We can see that as we reach the industrial age, the concentration of nitrogen oxides in the atmosphere has begun to increase. This data comes from ice core data and earlier projections. In the environment, when the nitrogen oxides are released, they can react with raindrops in the atmosphere to form nitric acid. We want to find out if the nitrogen oxide increase from about 260 parts per billion to about 320 parts per billion is responsible for any change in the concentration or the acidity of rainfall. Again, step 1 will always be define the system boundaries. I encourage you to write a little circle, a raindrop, a glass of water, whatever cartoon illustration you like, to write out your species list. In any aqueous solution, we will always start with this fundamental case. We'll start with water, hydrogen ion, and hydroxide ion in the pure water. To that, we're going to add some nitric acid. In this case, the maximum concentration in the atmosphere that's been measured recently is about 320 parts per billion by volume nitrogen oxide. That nitrogen oxide is going to form nitric acid in solution. The nitric acid is going to dissociate as a strong acid and form nitrate in solution, NO3. Next, we want to identify any species of interest. We're concerned with the nitrogen oxide in the atmosphere, but in the solution, we're concerned with the water, the hydrogen ion, the hydroxide ion, the nitrate anion, NO3-. We're actually not too concerned with the HNO3 because this is a strong acid and we know that it will completely dissociate. The next step is to write all the equations that may be relevant. In this case, again, a strong acid means that the HNO3 is going to disappear and we'll be left with nitrate and additional hydrogen in water from the nitrogen oxides that are in the atmosphere. They're going to change their form when they dissolve into solution, and that may affect the pH of our system. We can calculate the total concentration of acid in a raindrop from Henry's law. We can look up the Henry's law value for the nitrogen oxide and find that about 2.025 moles per kilogram, a kilogram, recall, is going to be have the same weight as a liter, so we're going to have 0.25 mole per liter per bar. Using Henry's law then, the aqueous phase concentration of the nitric acid is going to take the form of the dissolved nitrate gas in solution, and that's going to be equal to Henry's law times the partial pressure of the nitrate in the atmosphere. We always need to recognize and write down our simplifying assumptions. In this case, one of our assumptions is that all the nitric acid is going to form hydrogen ion and nitrate in solution, since we've noted as a strong acid. Then we'll substitute into our equation the Henry's law value, 0.025 mole per liter per bar. In this case, since we're in bar instead of atmospheres, we'll convert 1.013 bars per atmosphere. And we need to multiply that by the partial pressure of the nitrogen oxides in the atmosphere, which is 320 parts per billion, or 320 times 10 to the minus 9th atmospheres. Multiplying this out gives us a concentration of the acid of 8 times 10 to the minus 9 moles per liter. Note then that as we had previously, the total concentration is 8 times 10 to the minus 9. Since that must equal then the negative ion concentration of the nitrate in solution, that would be the approximate amount of hydrogen that we would have added to the solution, 8 times 10 to the minus 9. Now, recall the concentration of H plus in pure water is about 10 to the minus 7. Notice this is an order of magnitude or greater than 8 times 10 to the minus 9. Therefore, we find out that although the nitrogen oxides have increased in the atmosphere, and although they form nitric acid in solution, those nitric acid oxides globally have not significantly changed the pH of the rainfall, since 10 to the minus 7th is greater than 8 times 10 to the minus 9. Therefore, the pH of the rainfall, in this case, would be relatively unaffected. We'll see later that the concentration of H plus in rainfall actually does make rain acidic, but it's not from the nitrogen oxides. It's from other compounds like dissolved carbonates and sulfates in the atmosphere that change the pH of the rainfall.